Hi everyone. For the past semester, our team partnered with Inari to explore various methods for predicting unobserved gene expression values in maize plants. We took four approaches in total. The first two relate to feature selection and prediction, and the latter two relate to uncovering the underlying structure and network. Passing on to Sergio for our first approach.
So first, for our regression models, we use two different approaches to select the features for our gene predictions. So first, we use Gini3, which uses random forest regression to calculate the pairwise correlation between genes. Then for each gene, we selected as features the ones that have above 0.01 or more correlation. And second, we calculated the coefficient of variation of expressions of all the genes. We sorted them and we used the 1,000 most expressive genes as features. The models used were the following: linear, lasso, large, random forest regression, ARA boosting, and gradient boosting. Additionally, we used neural networks using dense layers with real low activation function. So even though the 1,000 most expressive genes method allows us to use the same features for all predictions, results were significantly worse than Gini3, as we got negative test R-squares as it happened with neural networks.
After our first approach, this revealed to us the need to better select features. We discovered the Connectivity Map project, which is a counterpart of our problem in the human genome. By selecting 1,000 landmark genes, they were able to accurately predict the expression values of the rest of the genes. Basically, they do unsupervised clustering and identify the centroids of the clusters as the landmark genes. However, we discovered that this method is unsuited for our large prediction task and our non-perturbation driven data. Because of the lack of the variability in our data, genes tended to be in large clusters. So each time we do the iterative peel-off to identify the centroids, we ended up removing the whole of the cluster, which makes us lose a lot of information.
We then opted to use more non-traditional methods, specifically using autoencoder neural networks. The first model being an autoencoder trained on the expression data in order to learn a lower dimensional embedding of this expression data, which would then be used for a regression task for predicting expression levels of genes. We then built an iterative variational autoencoder model, similar in concept to iterative PCA for imputation, where now we're using a nonlinear dimensionality reduction technique to update missing values in an expression matrix until a convergence criterion is met. While the autoencoder plus regression model did not perform very well, we found that our iterative variational autoencoder model did perform well, better than two other simpler imputation models at this imputation task.
Our journey thus far has led a more traditional approach into finding good accuracy, but we wanted to also model the true problem underneath, which is finding out the relationship between the genes. And we turned towards non-Euclidean methods, such as graph neural networks. And a lot of the research in this area is very cutting edge, but we ran into a number of issues as we fleshed out the model in terms of the different schemes in which you could construct such a non-Euclidean graph. A lot of this research has led to interesting discoveries and bug fixes with a close collaborator, Ramin Hasibi from the University of Bergen, on which we're doing continuous research now. Thank you for listening to our presentation.